Hello everyone, this is Haoyu Ma, a PhD candidate from UC Irvine. In this video, I will introduce our paper, CVTHead, one-shot controllable head avatar with Vertex-feature Transformer. First, we introduce the background knowledge of the 3D movable face model, commonly known as 3D-MM. The 3D-MM is a parametric model obtained from a dataset of 3D face scans. Through tuning the coefficients, we can explicitly control the shape, expression, pose, and texture of the face. However, the 3D-MM does not include the information for details such as hair, thus, it cannot be applied to generate realistic face images. To this end, recently, many research focus on training neural networks conditioned on the 3D-MM coefficients. Thus, we can generate realistic face images with details and achieve explicit control like 3D-MM. The input of the training datasets for these works can either be a single image, multi-view images, or videos. In our work, we are particularly interested in the setting with a single reference image. Specifically, we propose the CVTHead, which performs efficient and controllable head avatar generation from a single image with point-based neural rendering. The CVTHead takes a source image for identity and appearance, and a driver image for expression and head pose as inputs, and try to reconstruct the driver image during the training time. In detail, it consists of 3 components, including head mesh reconstruction, Vertex-feature Transformer, neural point rendering. In the next slides, I will go through them in details. We consider the flame model as the parametric model for the head mesh reconstruction. In detail, we utilize pre-trained Deca model to obtain the 3D vertex from both source image and the driver image. We can also use the pre-trained deformation model to augment the hair and shoulder region, but we found that this model is optional in our framework. By exchange coefficients, we can obtain the 3D vertex for both source and driver image while maintaining identical shape coefficients. Next, we want to obtain the feature vector of each vertex in the canonical space from the source image. A conventional approach involves implying pixel-aligned features, where the 3D points are projected onto the 2D image space, and aligned 2D features are selected from corresponding locations. However, there are several limitations for the pixel-aligned features. First, it requires accurate 3D mesh reconstruction to locate the correct 2D pixels. Moreover, when the 3D point is invisible in the 2D image, the feature and its 2D projection may not accurately represent the true features of that point. For example, in an image where the right ear is occluded by the face, the projection might still capture features from the right eye instead. To this end, we propose the Vertex-feature Transformer, which considers the vertex feature as learnable tokens, and the 2D projection as their corresponding positional encoding. And we concat both vertex token and the image tokens as the inputs to the transformer layers. Thus, we can solve the above issues of pixel-aligned features, and we can also model the long-range correspondence among all vertex features with the global attention. Lastly, we perform the neural vertex rendering with the obtained vertex features. We generate the vertex projection feature by projecting 3D vertex into 2D image space and align them corresponding vertex features with their 2D locations. We train a U-net to generate the driver image and also the foreground face mask. With this design, we can get rid of the tedious differentiable rendering in the traditional graphics pipeline. Here, we summarize the benefits of our CVTHead. First, it is a one-shot pipeline, which only requires a single reference image without any further fine-tuning or optimization for unseen subjects. In contrast to nerve-based approach that typically require multi-view images or video inputs, our method is more user-friendly and straightforward in practical applications. Secondly, our pipeline is significantly more efficient, requiring only a single forward pass for the rendering, as opposed to the volumetric rendering techniques that require hundreds of forwards per ray. Lastly, by learning the vertex feature in the canonical space, our method exhibits strong generation abilities across diverse head poses. In contrast, previous warping-based methods only work well for a limited range of poses. Here comes the results. As shown in these tables, our method can achieve comparable performance to state-of-the-art graphics-based methods such as RAW on both self-realignment tasks, where the source and the driver image come from the same subject, and also the cross-identity realignment, where the source and the driver image come from different subjects. Moreover, our method can bring much efficiency. Here are some examples for both self-realignment and cross-identity realignment. We can see that our method generates well on different unseen subjects and different head poses. Besides, we also show some generated examples of the same subjects with different expressions, face shapes, and camera views by adjusting the 3D coefficients. These results suggest that the learned vertex feature vectors does exhibit a strong alignment with the vertex in the canonical space. We also perform a ablation study that replaces the Vertex-feature Transformer with the pix-aligned features. We can see that when the point is occluded in the source image, the generated image tends to generate blur and shadow in the corresponding areas, where our method can successfully handle these cases. Alright, thanks for your listening. If you have any questions, please come to our poster with paper ID 216. Thanks.